Okay, so the next section, 4.6, the multiplication rule for independent events. So we're going to go over this. Sorry. Okay, so learning targets. We're going to use the multiplication rule to calculate probabilities. We will calculate probability of at least one using the complement rule and the multiplication rule for independent events. Determine if it is appropriate to use the multiplication rule for independent events in a given setting. So what happens to the general multiplication rule in the special case when events A and B are independent? In that case, we have the probability of B, given that A has already happened, will equal the probability of B, because knowing that event A occurred doesn't change the probability that event B occurs, right? So if you have two independent events, one won't affect the other. So we can simplify the general multiplication rule as the probability of A and B will equal the probability of A times the probability of B, given that A already happened. But the probability of B, given that A already happened, is just the probability of B. It says it right here. So it's just going to equal the probability of A times the probability of B. So this is only true for independent events. So the multiplication rule, this is more of the same stuff. In addition, the addition rule, probability of A or B, the probability of A plus the probability of B will hold if A and B are mutually exclusive, but not otherwise. Mutually exclusive, remember, is just they can't happen at the same time, right? Resist the temptation to use these simple rules when the conditions that justify them are not met. Okay, so the multiplication rule of probability of A and B equals the probability of A times B gives us another way to determine if two-way tables are independent. So we're going to look at that pierced ear example from earlier in the chapter. The following two-way table summarizes data from a college statistics class. Our events of interest where A is male and B has a pierced ear. Are these two events independent? No, they're not, because the probability of A and B, if you were to find their probabilities, they are not equal to each other. So the probability of A times the probability of B equals the probability of the male times the probability of B, or the pierced ear, which is 0.297. So since these two are not equal, then they are not independent. So the next one here, you play tennis with your friend every week. From all of the past games, you know that each game is independent, and you estimate that they have you a 60% chance of winning any one game. If you play two games against your friend next week, what is the probability that you lose both games? Okay, so if you win, that's 60% chance of winning, so that means you'll have a 40% chance of losing, right? So all you're going to do is just multiply those two events, right, because they're independent. So our answer would be 0.16. Okay. Assume a randomly chosen battery has a probability of 0.8 of working. A remote control requires two working batteries in order to work. What's the probability a remote control will work if two randomly chosen batteries are put into a remote control? So what you want to do here is just go ahead and multiply, right? Two randomly chosen batteries, so 0.8 times 0.8, which is 0.64. That would be your answer. Okay, a statistics teacher announces to the class at the beginning of the semester that there's a 40% chance a randomly chosen student will finish the semester with an A in the class. And there's a 60% chance of 60% a randomly chosen student will get an A on a test during the semester. Is the probability that a randomly chosen student receives an A in the class and an A on a test during the semester equal to 0.24? Okay, so for this one, let's look here. We have yes, the probability, or because the chance of getting A on a test and getting an A in the class are mutually exclusive. Remember, mutually exclusive means they can't happen at the same time, right? Or no, they're not mutually exclusive. Yes, they're independent, or no, they're not independent. So the solution to this is D. No, because the chance of getting an A on a test and getting an A in the class are not independent. There will be people in the class that get that 40%, that have a 40% chance, who are in that 60% chance range, right? So there are some people that could, who can finish with an A, that who are also in that 60%, who can get an A on the test, or during the semester, sorry. So that's why they're not independent, because you can actually get an A on the test and get an A in the semester. Okay. A die is rolled and a coin is flipped. The probability that the die lands with a 5 up is 1/6. The probability that the coin lands with the heads up is 1/2. Is the probability that the die lands with a 5 face up and the coin lands heads up equal to 1/12? So A, yes, because the die and coin are independent. They're not independent, they're mutually exclusive, or they're not mutually exclusive. So we're not dealing with mutually exclusive. Remember, mutually exclusive means they can't happen at the same time. These two things can happen at the same time. So that means that we would either have independent or not independent, right? Does one depend on the other? Does rolling or flipping a coin depend on rolling a die? No, it doesn't. So these two events are independent. Okay, next, you play chess with a friend, and from past experience, you know each game is independent of each other, and estimate the probability of winning any game to be 0.6. If you plan to play 3 games against your friend, what's the probability that you win at least one? That you win at least one of the games. So to do this, what is easier is if you figure out the probability of losing all 3 games. So that would be 0.4 times 0.4 times 0.4. Okay, and that's 0.064. Okay, so this is the probability of losing all 3 games. So probability of L, L, L. Okay, now to find that you will win at least one, right? All you have to do is do 1 minus the probability of losing all 3, right? Because if you do 1 minus the probability of losing all 3, that will give you the percentage of winning at least one of them, right? So 1 minus 0.64. I'm sorry, 0.064. And that is 0.936. So D would be your answer for that. Okay, so when you see this, winning at least one game or something like that, find the probability of losing in this particular case, it's just losing all 3 games, and then you're going to do 1 minus that probability, right? Because if you're losing all 3 games, you're not going to win at least one. But if you do 1 minus that, then you know you have at least the chance of winning 1. Okay. Next slide here. Of all the light bulbs manufactured at a certain factory, 95% of the light bulbs work and 5% are defective. If 6 light bulbs are selected at random from the shipment, what is the probability that at least one of them is defective? Okay, so again, at least one of them. That's a key word here. So we want to find the probability one of them is defective. So, well, let's find the probability of all of them being, if all of them work, right? So, and we have to do that 6 times because it's 6 light bulbs. So working 6. So I've got W's for working. And 95% is that work, so 0.95. And I'm just going to raise it to the 6th power. It's the same as multiplying it out 0.95 by 6 times. And what we get there is 0.73509. We'll just leave it at 0.735. So what I'm going to do is I'm going to take 1 minus the probability that all 6 work. Okay? Remember, if all 6 work and we're trying to find one of them being defective, all you have to do is do 1 minus that, or 1 minus 0.735. Okay, and 0 minus 0.735 is 0.265, which is B. Okay, I believe that's the end of our notes. If you do have any questions, please don't hesitate to reach out.